Don't we have to switch to the PC to record?
No,
it can do it
it does it independently. It's a black box connected up to this thing.
Okay.
Do you want the microphone?
Okay. He said something about introducing me, but that's all right. No, don't worry. I can introduce myself. It's fine, right? Yeah, I'm fine. Hi, my name's Rajeev Gore. I'm from the Logic and Computation Group here at the Research School of Computer Science. I'd like to tell you a little bit about practical reasoning using logic. So I was but listening to Pascal's talk. So in some ways, this is a similar application in that I'm going to show you, well, what I'll do is I'll show you, I'll outline some real problems from the real world and describe what the problems are without using jargon. And then I will try and show you how we can solve some of those using logic and computation. Then I'll tell you a little bit about our group and what's involved in logic and computation research. I'll mention some connections, how you can join us, and I'm hoping to finish off with a demo that shows you the application of some of this work that we've been doing here. This is supposed to be, an information talk or whatever, so please stop me at any time and ask questions, right? I'm not going to go all the way till 5:2. I mean, depends. If you want to ask questions, I'm happy to stop and explain something. Little bit of background knowledge. Can you tell me how many of you are doing a computer science degree? How many of you are doing a maths degree? Philosophy? Anyone else?
Network security.
Network security. Science? Okay. So how many of you have seen, so your third years? Second years? First years. Okay, a mixed bag. How many of you have seen some logic, like and, or, not? Okay, pretty good. So is it formal logic or digital logic? Who's seen digital logic, as in digital circuits? Right, and who's seen formal logic, as in, great, okay, fine, we're going to be, all right. So here's how we might try to reason about digital circuits, right? So you've got a digital circuit, you've got a wire called A, a wire called B, a wire called C, and there are two inverters in between. So what does an inverter do? The inverter X says, whatever the signal is on A, I will invert it. And this guy says, whatever the signal is on B, I will invert it. Now we're talking digital circuits, so the signals are either high or low. Those are the only two choices, right? So this guy is basically saying, if A is high and the gate is okay, then B will be low. And I'm representing low by a negation sign. Is everybody comfortable with the syntax that I'm using there? Right? Okay, so if you're not, this stands for conjunction, and this stands for implication, if then, and this stands for not. All right? But I don't want to go into the details of that for the moment. So the problem we have is we have a knowledge base, we see that A is high and C is low. Is this normal behavior? Right, so Pascal, I think, was talking about diagnosis of faults and things like that in networks. Right, this is an example. So if there's a fault, you want to try and locate where the fault is, but first of all, you have to, say that something is faulty or not, right? So we observe that A is high, C is low. We have to figure out whether this is abnormal or not first before we do anything. So that's one. Another one, I'm going to let you read this first. Okay, so who knows what public key encryption and public key RSA, that sort of stuff, right? Public key communication. So some of you know. So what I've written up there are standard steps that, for example, your browser does when you want to do banking. When you want to do secure banking, right? Your browser is communicating with the banking software using encryption, but, you know, it's an arbitrary bank. How do you know what its public key is and how can you communicate it with it, right? So this infrastructure is out there. It's RSA is one form of it. These 7 steps I've deliberately written in English because I could have written them in, you know, some complicated technical jargon which the cryptographers use, but even I can't understand that, right? So the idea is, you know, A and B are trying to communicate. There's a trusted server, and they use this public key cryptography infrastructure. I don't want to go into the details, but basically what it is message passing, right? There's a bunch of messages that are being passed, and they're being encrypted using keys. So each of these has a key, has a private key and a public key. And basically there's some encryption going on, and this is called a security protocol. So the idea is that when A and B reach the 7th step, then A and B know each other's identities. They know these secrets, NA and NB. And the main thing is that eavesdroppers don't. So C, who's listening in on these channels, doesn't know what's going on, right? Because all of this stuff is being done over the internet with packets, right? So it's very easy for someone to be sniffing the packets. So the fact that there is likely to be an intruder listening in on your conversation is almost one, right? But what you have to guarantee by these steps is that it doesn't matter what they listen to or how many times they listen. They don't know these secrets. Looking at that, can you tell whether it's correct or not? Does it do the job? Right? So how do we design this protocol, and we want to assure, you know, the bank of whatever wants to assure its users that eavesdroppers aren't listening. What can it do? How can it convince you? Now, at the moment, what they say is, trust us, right? But that's not the game that we want to play, right? We want to be able to prove rigorously that it's safe. So this will be an example that I use as well. Now, talking about the banks, after the GFC, the banks, the ones that survived, got hit by a lot of anti-fraud legislation by the governments. The government said, we don't want this to happen again. You've been too lax in your house lending, in your risk analysis and whatever. So they imposed a lot of rules and regulations on banks. Now, the rules and regulations have been trickling down to the bank employees. And this is a made-up example, but this is the sort of stuff that goes on in their processes now, right? So there are rules. Someone requests to open a bank account. Well, you've got to do a risk assessment eventually, right? Someone requests to open a bank account. You only grant it if you assess the risk to be low. Someone asks to open a bank account. You've got to do a due diligence assessment. And if the person fails due diligence, then they've got to be blacklisted. So these are the sorts of things that they do. You've got notions like risk assessment, request to open a bank account, due diligence, blacklisting. Now, you could write this in formal logic, but you don't want to, because normal people have to understand it, right? Your bank employees have to be able to implement this stuff. So you don't want to write it in Greek symbols, unless you're in Greece, of course, but you know what I mean. So what do you want? But you want to check these to make sure that they're sane. So first of all, they have to be consistent in that, you actually have to be able to go through this and request a bank account and get one. It's pretty stupid if, every request is denied. It's very safe, but you're not going to have many customers. And then the other one is sanity, in the sense that how do you know that there isn't a way that someone can sneakily get a bank account? Right? Consistency says, it's okay, someone will get a bank account, but sanity says, no, it's safe. It's people that shouldn't get a bank account shouldn't get one. Another way, you've got a compiler that's compiling safety critical code for REN5 or REN4, which one was it? I can't remember. There's the original code, there's the compiled code. Prove that the two are equivalent. All right? Because safety critical people could die if you get it wrong. Or your rocket could blow up like REN4 did. Or was it 5? I can't remember which one. There was some bug, and it went into an unsafe mode, and they had a safety thing which said if such and such happens, then the rocket has to be detonated because it's unsafe. It might come down on people. All right. Finally, web applications are everywhere. Now, suppose you want people to have some access, but you want to limit the damage that they can do. Now, think of your smartphone. Right? This is the sort of stuff that you might want to do on a smartphone. Again, I'll let you just read that. So what are these things trying to do? They're trying to say, you don't want to download an app that looks at your private contact list and then sends it to, XYZ marketing or something like that, right? So this is the sort of stuff that you can write to try and limit what your app can do. And there are some really nasty malicious apps out there. So for example, we know that there's one example where you download an app and it's completely harmless because all it asks you for is internet access. Right? It says, I don't want access to any of your private data, I just want internet access. You say, okay, fine. And you're browsing away and you download another app, you don't know that they're related. And it says, I want access to your contacts list. You say, yeah, sure, it doesn't have internet access, I'll give it access to my contacts list. Now these two apps have been written in a malicious way so that when they're on the same phone, they talk to each other. And one of them sends the contacts list to the other, and the other one sends it out to the internet. Right? So these exist. This is the sort of stuff that you can do to protect yourself, right? If you could have a monitor monitoring these apps, then that sort of communication would be forbidden. Right? We're actually working on that. We've got a PhD student working on that. Okay, so now I'm going to go over a little bit of classical propositional logic and show you how we can tackle some of these problems using logic. So first of all, why do we want formal logic? Well, it's exactly the reason that I showed you. If you try to reason about these sorts of rules using English, you write pages and pages and pages of prose, right? And you just get lost. So what you need is a language that is formal, that is succinct, and captures this with the minimal amount of overhead, so that you can look at it and say, oh yeah, I know what this means. I know exactly what this means. Whereas some of this stuff, might be interpreted in slightly different ways. Okay, so that's why we want formality. So, who's seen Bacchus-Naur form? All right, not many of you. So I'll just explain this. So classical propositional logic in the Western world is about 2,000 years old. And what it's trying to do is it's trying to capture the meaning of the basic connectives not and or if then and if and only if that we use in natural language. Right? So what it's trying to do is it's trying to model natural language. That's where it comes from. So we have a syntax. What does that mean? It means we have a special language for writing down formulae which is different from natural language so that we can tell, oh, this is a formula. So what does this say? This says P is an atom, Q is an atom, R is an atom, and we have some typically infinite supply of them, but I only need a couple for the moment. What does atom mean? It means you can't break them down any further. Right? So P is something, and I'll give you an example in a minute. It's some statement, and it'll either be true or false. That's what the classical means. In our group, we study non-classical logics. I'll give you an example in a minute. So, this is by no means, this is like the basic logic that we start with and we extend it in various ways. So P, Q, and R are some basic statements which you can't decompose any further. And then how do you build formulae? you say, well, every atom is a formula. So P is a formula, Q is a formula, R is a formula. And then if you give me a formula, I can negate it. If you give me two formulae, I can conjoin them. So this is and, there. If you give me two formula, I can disjoin them. So this is or, inclusive or, phi or psi, means phi is true or psi is true, or both. This says if phi is true, then psi is true, and this says phi is true exactly when psi is true. Phi is true if and only if psi is true. So you may have seen a different syntax in your lecture notes, where you come from. People might use a different symbol for this, a different symbol for this, but this is the symbols I'm going to use consistently. All right, so we've got a syntax, but what do these things mean, right? There's not much point doing this unless we all agree on the meaning, right? Because what we want is we want the bank people to have a particular meaning, and we want to have exactly that meaning. Otherwise, we're talking cross purposes. So what do we talk about? We talk about models. So what is a model of a formula? It's an assignment of the truth value true or else false to every atom. Right? Every word there is important. It's true or else it's false. It can't be both, and it can't be neither. Right? So, as an example, let the atom P stand for I have a brother. All right? Can you please put up your hand if you would make P true? All right? Each one of those is a model for P, because they make P true. Okay? Some of you didn't put up your hand. You're still models for P, it's just that you make it false. Right? Now, if you think about it, there were 6 or 7 people that put up hands and 6 or 7 people that didn't. But if you think about it, how many different models can there be for the formula P? Different models. There are the ones that make it true and the ones that make it false. Right? So although there were 6 or 7 people that made it true, all of those people are essentially the same model. They make P true. And the ones that made it false are essentially the same model. They make it false. Right? Okay. Here's another example. More complicated. So the formula is something implies something. Right? There's that main implication. Then I go on the right and I'm looking for a formula. Is Q a formula? Well, yeah, it's an atom, and atom's a formula. So the right-hand side, I'm happy. On the left-hand side, what have I got? The main connective is a conjunction, so I need a formula on the left and a formula on the right. I have got a formula on the left, because it's an atom. Have I got a formula on the right? Oh, well, the main connective is an implication. Come back here. I need a formula on the left and a formula on the right, and I've got them. So you could do a parse tree. That's why I talked about Barker's announcement. So you can tell whether a string is a formula or not by parsing it according to these rules. Okay, let's look at the assignment that P is assigned true and Q is assigned true. So what am I doing? I'm just going to fill those with trues in all the spots because both P and Q are true. Now I'm going to do a little bit of computation. So let's look at true implies true. If true, then true. Sounds like true to me, right? So we'll replace that with true. True and true. Well, that's true. So I'll replace that by true. True implies true evaluates to true. So I'll replace that by true. So what's the conclusion? This formula evaluates to true in the model that makes P true and Q false. Right? So that's one way that we can evaluate the truth value of a formula. Please feel free to wander around if you prefer to go to the other lecture. Right? I don't have a problem at all. So you can walk out at any time. Now I'm going to try and give you a little bit more formality and give you some jargon, but it shouldn't be frightening. So what I talked about a moment ago, these models are called the semantics. It's the meaning of formulae. And we have two important notions. One is called satisfiability, and it says phi is satisfiable if phi is true under some assignment of truth values. right? Let's take the formula P. Is it satisfiable? Right? That was the one where it said, I have a brother. Is it satisfiable? Yes. Why? Because at least one of you put up your hand. That was it. Right? There's at least one model that makes it true. Valid is a stronger notion. It says every valuation has to make it true. So if I take the formula, I have a brother, P, is it valid? Why?
There are some that come from the table.
Right? So there were some people that didn't put up their hand. They made it false. Right? So if I interpret P as I have a brother, it's not valid. What if I said P or not? Let's say Q says I have a sister. So P is I have a brother and Q is I have a sister. And I ask you P or Q. Who's going to put up their hand?
Everyone.
Depends. Still not valid.
Why not?
Because some people may have their siblings.
Right? Right? P says I have a brother. Q says I have a sister. But if you're an only child, you can't make that true, right? What about P or not P? I have a brother or I don't have a brother. Right? Unless you start doing some, I don't know, adoption and whatever, siblings and whatever, you know, if you get into the fine grains, you might be able to make it false. But P or not P is generally valid. So we know that there's at least some formulae which are valid, right? So it's not a vacuous definition. And then these two are actually connected in this way, but I'm not going to go into that in any detail. All right? Okay. Here's our example again. That formula is satisfiable. Why? Because the definition says it's got to be true under some assignment. And on the last slides, I just showed you that it evaluated to true under this assignment. Right? How difficult is this problem? If you want to know whether it's valid, you have to check all the assignments for n atoms, because this formula will in general have n atoms across the bottom, right? N atomic formulae. In this case, n is 2. So how many truth valuations do we have? Right? True, 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 false, false, true, false, false. Okay, that's pretty easy, right? But this is one of those problems that Pascal was talking about that grows exponentially, right? So I just want to demonstrate to you. So suppose I have 10 atomic formulae, right? How many valuations do I have to check to conclude validity? 1024. Yeah, sure. Modern computers, quad core, blah, blah, blah. We can do that. All right, let's double it. Suppose we want to talk about 20 propositions. Digital circuit with 20 wires. 1, 2, 3. That's about 1,000,000 and something, right? Again, yeah, we might be able to do that on a computer. But, you know, a digital circuit of size 20 isn't particularly complicated, right? This thing probably has, 1,000,000 components to it. So let's try 2 to the 30. 1,073 million. Now I'm not so sure that I can do that in, right? Let's try 2 to the 40. 1, 2, 3, 1,099 million or something like that, right? What about 2 to the 100? I'm not going to be able to do that on a computer in any reasonable amount of time. I think actually 2 to the 100 is something like the number of atoms in the universe or something like that. I may be wrong about this. It may be 2 to the 1,000, but that's a very big number. And you're going to be waiting forever if you're going to do this in this dumb way, checking all 2 to the n assignments. So Pascal was talking about branching and pruning. Right? So this is where this branching and pruning can come in. You've got so many choices, you can't possibly cover them all. So you have to come up with clever ways. I'm not going to go into the details, but basically the question is there a purely syntactic way? What do I mean by that? What I mean is you look at the formula and you have to just decompose the formula and do something with the formula and get an answer. Whereas this was a semantic way, right? What it said is, I know that the formula is made of 20 propositions. I'll just go through all the possibilities, right? That was using the meaning, true or false. Where what I mean is use the syntax only. What's the structure of the formula, right? That leads me to what we do. So our area of research is called automated reasoning. And the general idea is you're given a formula in some logic, and you have to decide whether it's satisfiable or valid efficiently using purely syntactic methods. If you can use semantic methods and do it practically, that's okay too, right? But in general, as I showed you, you probably won't be able to. So input is a formula phi, an answer, satisfiable or unsatisfiable. And ideally, if it's satisfiable, then you want at least one assignment that makes it true to prove to the person that it is satisfiable. Sometimes for some applications you want all assignments. And ideally, if you say it's unsatisfiable, you have to give a proof of why it's unsatisfiable. So the idea is you give something back so that the person can check your answer. That the person doesn't just have to rely on you being right. So here's our knowledge base again. Now I want to talk about the logic. So this thing captures the behavior of this gate. If A is high and the gate is okay, then B is low. If A is low and the gate is okay, then B is high. And similarly for B and C. Right? That's a bunch of logic formulae. We observe A and C. What can we do? Well, we can take that, add A and not C. We'll set the gates to be okay because we want to see if the formulae are all right. So we'll set that the gates are okay and we'll pass it to a satisfiability algorithm. I'm not going to go into the details, but it was one of the things that Pascal talked about, constraint programming and things like that. It's a branching thing, it cuts down the branches and it gives you an answer. But it's an exponential problem, right? Now, do you want to be hanging around waiting for the exponential problem? No. What you want, and this is the research that one of our, Jinbo Wang does, one of our members, he says, fine, you give me a knowledge base and I'll spend a bunch of time compiling it first because this is the knowledge base that's fixed. Okay? And then he invents special structures into which you can compile this such that when you ask a query, it answers it in polynomial time, the size of your query. All right? So they've done lots of research on what's the best way to store this information, and there's a whole bunch of papers on that if you want to look that up. Yeah?
So they're using optimization techniques to get what they think is
This?
Yeah.
No. What they have is that they have a theory of normal forms for storing this information. Right? So what they do is they mangle the formula into certain forms so that these queries can be run faster. And the normal forms have certain redundancies in them, right? So that some operation is very fast, another operation might be slow, so you build in some redundancy which makes this operation fast as well, right? But the main thing is that you have a lot of time to do this, right? It might take you a week to do this compilation, but once you've done it, your answers are really quick. Okay? Any other questions? No? Okay. So now I'm going to show you some work that we did on these banking rules. So what we did is we said, let's these things be atomic formulae, right? RA means that we've done a risk assessment. So it's either true or false. RO means we've received a request to open a bank account. So it's either true or false, and so on. The request is granted, true or false. Risk assessment is low, true or false. Due diligence is done, true or false. Request to open a bank account. Due diligence has failed, true or false, and the person is blacklisted, true or false. Right? But we need more. Classical logic isn't enough because we've got these guys hanging around. Eventually, only after, before, those words are in there as well. Right? So what we need is we need to extend classical logic with some temporal notions. And I'd like to tell you a little bit about that now. So this is called linear temporal logic. What do? You take good old classical logic, you've seen it before, and you add extra operators that allow you to talk about time. So this says that phi is true in the next state, the next moment in time, tomorrow. This says phi is true until psi becomes true. This says phi is true before psi is true. This says phi is true at all time points in the future. And this says phi is true at some time point in the future. I'll come back to these in a minute in the demo. All right? Now, all I've done is I've given you some syntax and sort of an intended meaning for what they are, right? What do I need to do? I need to tell you what the models are. So what are the models? They're sequences of points, linear sequence of points, S0, S1, S2, and each one of them assigned true or else false to each atomic formula. So it's what we had before, but instead of having only one, there's one at S0, there may be a different one at S1, there may be a different one at S2, and so on. So if we take this I have a brother example, right? The idea is that it could be true in state 0, or it could be false in state 0, it might be true in state 1, it might be false in state 1, and so on. Right? So the truth value changes as time goes on. So that's the idea. How do we evaluate them? Well, we can evaluate at a single state using the classical propositional logic stuff that I showed you, and we evaluate the temporal formula using the relative order. I'm not going to go into the details. There are papers on this which we've written. You can look on my homepage if you want. Again, there are these notions, satisfiable. Phi is satisfiable if there's some linear sequence and some state in it that makes it true. It's valid if it's true in every state of every linear sequence. So we're getting more complicated. And there's this lemma about validity and satisfiability. All right, here's our example. At all time points in the future, if we receive a request to open a bank account, then eventually you have to do a risk assessment. At all time points in the future, if you're going to grant the request, then you better make sure that the risk assessment is low. At all time points in the future, if you get a request to open a bank account, then eventually you have to do due diligence. And at all time points in the future, if somebody fails due diligence, then eventually they have to be blacklisted. Is it safe? Can you tell? Right? We've coded it up. Are these rules same? What do we need? We need to somehow check that these things make sense. So I'll come back to the demo for that. So this is the sort of research that you can do in logic and computation. Right? You could design a new logic for reasoning about whatever, right? Your Facebook friends. Or you could, given a logic, you could look at better ways to decide whether something is valid or satisfiable. You could use computers to actually do the proof. You would need to do a computational analysis to say, you know, how complicated is my procedure? Is it polynomial time? Is it exponential time? It will be exponential time because none of these problems are easy. Can we extend the logic with maybe arithmetic so that we can reason about Pressburg arithmetic or piano arithmetic? Implement a prototype. Make that prototype competitive with existing methods, or show that it can be extended to real-world examples. And so there's an element of experimentation. And of course, at the end, if you can, you want to commercialize your technology. Why am I here? Because I'm not very good at this last step. So I'm working on it. Okay, so other areas. Artificial intelligence. You have an agent and you want to extend it by notions like belief, knowledge, and desires and intentions. It believes that something is true, which is different from it knows something is true. It intends to do something, which is different from it desires to do something. Right? So these logics can be used there. As I said, Pascal talked about fault diagnosis, so we can use these logics there. There's constraints. Software verification, you can verify a microkernel using this technology. It's been done at NICTA, or it has been done at NICTA. Some of you may have heard the word ontologies, right? So ontologies are the logics that they use in ontologies are very close cousins to this temporal logic that I showed you. They're called modal logics. Discrete event systems, you want to control aeroplanes at an airport and keep them in a holding pattern such that each one of them is 1,000 metres apart in vertical distance and, 1,000 metres apart in horizontal distance, and you want to do this automatically. But aeroplanes obey physical equations, which are dynamic. But we're using a computer, which is discrete, ones and zeros. So how do you capture the dynamic behaviour using a discrete computer, right, rather than analog devices? You probably know about software engineering, program verification, but the more interesting one is synthesis. I write down a specification in Logic of the program, press a button, and it generates the program for me. Right? That would be the ideal. And there are even, some of you may have heard of functional programming languages like Haskell or OCaml, right? If you dig down into their roots, it's all based on logic. Right? They are based on the fundamental principles of logic. Okay, who are we? We've got a bunch of people here. Hardly anyone comes from Australia, and hardly anyone has done their PhD in Australia, so we're fairly diverse. We've got a bunch of, again, diverse PhD students. They go to interesting places to do their postdocs, and we're always looking for more PhD students. So if you want to find out more, you could look at our web pages. We've got a formal methods for software engineering course. We've got a logic course, foundations of mathematics course. Every year we run a logic summer school. So if you're in, say, second year or third year, look on our homepage, and we'll be holding one in December. I think that the applications are still open. So if you want to apply and come for 2 weeks of wall-to-wall logic in early December, that's the way to do it. We can design independent study projects for you, assuming that you're ANU students. Just ask. We may even be able to do it if you're not ANU students, but then it gets a bit harder. Just to leave you with those while I can't set up my demo at the same time, but the digital circuit is flawed, right? Because if A is true and it works properly, then B should be false. And if the inverter works properly, if B is false, then C should be true, because it's inverting every time. The banking rules are faulty because way back here somewhere, we wrote all this stuff about due diligence, whatever. But we forgot to say what blacklisted means. Blacklisted means don't give them an account, and we never said it, right? So, our tools can actually find this bug, and that's what the paper was about. Security protocols. That security protocol was designed in 1983, and it remained intact until 1995, I think, when a guy called Gavin Lowe at Oxford found a bug in it. There is an attack which nobody had discovered for 15 years. So now he fixed the attack. It's called the Needham-Schroeder-Lowe protocol. Look that up in Wikipedia. It's a really interesting case study. And the bug was found using logical methods. If you're interested in anything, feel free to email me. Okay, I don't know how much longer you're here. I think you're only here for the weekend, right? Monday as well? Okay, Monday's a public holiday, so, I'm enthusiastic, but I won't be around, right? Feel free to email me about anything, right? If you want information about the Logic Summer School, whatever. And what I thought I'd do now is just show you a little demo. Again, if you have better things to do, please feel free to walk out. I'm not going to get in the least bit offended. Okay, so I told you about this PLTL, this temporal logic, all right? How can I convince you that the computer understands a temporal notion? Say the days of the week. One way would be if it could draw you a diagram, if it could give you a model of the days of the week. All right? So this is what this demo is about. So there's a theorem prover written by one of my students. It's called PLTLPS, and I'll show you in a minute. So I'm going to run that theorem prover, and I'm going to run it using a shell script. So where is it? PLTLPS. I just want to show you the shell script first. Right? Nothing up my sleeve. That's what it does. Right? It calls the theorem prover with some options, moves some file called idiot.ps so that I know when I've done something wrong. It flashes up that you're an idiot, but don't worry about that. There's a sed script which removes lots of guff, and then it produces a dot file, and we call the dot graphical package, and it creates it creates a dot file, and then I'm going to use Ghost View to view that. Right? That's all that the shell script is doing. And whoops. So what am I going to do with it? I'm going to try and model the days of the week. How am I going to do it? So I'm going to give you an example. So here's the days of the week where we begin. So I claim that these formulae capture some aspects of the days of the week. So there are 7 propositions, atomic propositions, Monday, Tuesday, Wednesday up to Sunday. Right? So each one of those is going to take the value true or false. Obviously, if it's Monday, Monday is true, and so on. Then G says at all time points, ampersand says and, equals greater than says implication, and X says tomorrow. So what does the first thing say?
If it's Monday, the next day is Tuesday.
Sorry, say that again.
At any time point, if it's currently Monday, the next day is Tuesday.
Perfect, right? At any time point, if today is Monday, then tomorrow is Tuesday. Make sense? Yeah? And the others are the same, right? All the way down to if today is Sunday, then tomorrow is Monday. So I've built in the fact that the week wraps around. Okay? I'm going to ask the theorem prover to give me a model for this. So what is it going to give me? It's going to give me a sequence of time points such that each one of these formulae is true according to the definition. Now each one of these formulae has got a G out the front, which means it's got to be true everywhere. Right? So it's going to give me a linear sequence where each one of these inner formulae is true everywhere. If today's Monday, then tomorrow is Tuesday. If today is Tuesday, then tomorrow is Wednesday. So on, right? Okay, let's see what it does. So I say dot slash PLTLPS less than e.g. week 1 text. What have I forgotten? No such file. What do you mean? Oh, I misspelled it wrong. So this is why I need that. PLTLPS less than. What have I done?
Second half.
Ah, I misspelled it, did I?
Yeah.
Ah, PL. Okay, fine. All right, can you see that up the back? So it says, here's the model. The first world, nothing is true. And in the second world, everything is true.
So you didn't say that it has to be a day.
Didn't have to be.
You
So
didn't say that it has to be a day.
it has to be a day. What do you mean?
One of those days.
Right. Exactly, right? So the first problem is that I didn't say that today has to be one of those days. Right? So it says today's none of them. Great, fine, right? All the statements are still true. And I just want to show you what it did. There's some stuff here about fonts, but what did it do? It took the formula, right? Then it put it into some sort of special normal form that it has. Basically what it does is it just gets rid of all these implications and converts them into disjunctions and pushes negations aside. It says it's satisfiable, meaning I've found a sequence which makes them all true. It took me this long. It's doing some other stuff. And it generated 9,260 nodes in doing so. Right? Fine. So there's something wrong with this. How are we going to fix it? Well, here's one way. Where's my Emacs file? So I'm going to go to week2.txt. What have I done?
You said before time was has to be one of the day.
Right, so what's it going to get rid of? Which problem is it going to get rid of?
We know that those
Right? Because the no state said, oh, it's none of them. It's Monday's false, Tuesday's false, they're all false. What this says is, no. One of them has to be true at every time point. All right, so let's have a look. So this is the safest way because I know that it works. Voila. Right, so we had, where's my first one? Right, that was what we had. We added the fact that it has to be one of the days of the week. So it says, fine, today's Sunday, but tomorrow is Sunday too. Now, there was a rule that says if today's Sunday, then tomorrow is Monday. Well, yeah, it says, fine, today's Sunday, tomorrow is Monday. What's your problem? But tomorrow is Sunday too. You have the answer. Right?
Well, I guess so.
Sorry?
I didn't.
Can today be Monday and Tuesday?
Oh no, but so how would you just like X
Right,
not-
so we need an XOR, right? Right, we need to say, so that OR that we put in, so where was the OR that we put in? Where's my Emacs? So this OR that we put in is inclusive, right? It says Monday or Tuesday or Wednesday. It doesn't say only one of them, right? Each day has to be one of them, but it has to be exactly one of them. It can't be more than one of them. Now, this is where our syntax gets in the way a little bit, because classical logic works with inclusive OR, right? But look at the trouble I have to go to make that exclusive OR business. Right? It's a little bit, well, it's not very nice, right? But I could define, an exclusive OR connective as well, right? And add it to the system. I just chose not to do it.
I just saw it, that brings up the power of multi-input exclusive or something like that. Yeah.
Multi-input exclusive OR.
Because
It'll be it'll be complicated. No, you're right, yeah. Because A or binary is easy, right? But multiple, no. So don't worry about how I need to do it if I want to give an internal definition. I can do it using the syntax of what I've got. So what does it say? It says, at all time points, if today's Monday, then it can't be any of the others.
Is that the type of one going?
I hope not.
In the first one, there's
It's an extra space.
Extra space?
Winston.
Oh, white space doesn't matter. So we can get rid of it. There we go. Right? So the first clause says if today's Monday, it can't be any of the others. If it's Tuesday, then it can't be any of the others. Wednesday, and so on. Right? So let's see what we get. Where's my... So I want that, but I'm going to go week 3.
So it's saying it's Monday and not Sunday, not Sunday, not Sunday.
Right?
that's okay.
It makes sense, but it's like it's just word.
Yeah.
It's a model of the week, isn't it? It says if it's Monday, then it can't be any of the others. If it's Monday, then tomorrow's Tuesday. If it's Tuesday, it can't be any of the others. Then Wednesday, Thursday, and look, it even wraps around to Monday again, minimally, right? Well, what it could do is it could give you an infinite sequence, which says, Monday to Sunday, Monday, Sunday, Sunday, right? But it's clever enough to say, no, I detect a repetition here, right? So this is part of, that was actually one of the major problems with building this theorem prover, because you get these infinite loops all the time, right? Beg your pardon?
We built it.
My student, Jimmy Thompson, built it. He's writing up his PhD and he's off to Microsoft Redmond. So he's selling his soul.
Yeah.
Okay. Now, one final point. So is today Monday? Right. How can I fix it?
What an initial statement.
Which says what? What day is today? Good question. So I just want to show you the last one. It's just a refinement which will need to be fixed because I gave this lecture on a different day to my other students. So what if we just say today is Saturday? It is Saturday, isn't it?
Yes.
Right. So let's go here and we'll try week 4. Right, so all it's done is rotated everything around, so it starts on Saturday.
So the top state is the...
Say the beginning, right? Yeah, right. I mean, I could have done it the other way, but I just chose to do it this way, right?
Okay.
So if you think about, have you heard of the sort of artificial intelligence test? The idea of when do you judge something to be artificially intelligent, right? So this thing is able to model the days of the week purely by putting in some abstract syntax of this form, right? And all I'm doing is doing pure logic. So I haven't told it anything about, days of the week in any concrete sense. All I've told it is the relative order of some propositional variables and use the meaning of the underlying connectives in the logic to extract this information, right? So this is, the computer has a notion of the days of the week that we can work with, right? I'll stop now and take questions if you want. I'm happy to hang around afterwards if you want to play around with this. Yep.
What is the idiot PostScript file?
The idiot PostScript file. Okay, the idiot PostScript file is done this way to remind me. So it's idiot.tech, and it says always idiot, right? So if I run it, where am I? TXT. Right? So I just build it in because if I misspell something, then I want this to come up, right? But I misspelled it, but it didn't come up because I mistyped PLTL or whatever, right? So, any other questions?
So, is temporal logic used in concurrency?
In
Concurrency,
temporal logic is used in concurrency if you want to model a linear sequence of time points, right? So the most useful example that I can give you is digital circuit verification. So Intel has a whole lab of people trying to verify digital circuits and check them using these temporal logics, okay? Because they don't want another Pentium bug.
Yeah.
And hiring a bunch of logicians is cheap. It doesn't cost you $500 million, right? And they really do. One of our lecturers from here in 98 or 2003, I think, was an expert in this stuff, and he went over to, are they based in Seattle? Is Intel based in Seattle? I'm not quite sure where it is. They have a lab on the West Coast, I think it's in Washington, and he's been there, and this is what he does. He does digital circuit verification using temporal logics and logic-based methods. Now, there's a cousin of this called computation tree logic, which looks at branching time, right? So time isn't necessarily linear, but time is allowed to branch. But it's still discrete in the sense that you go to a next state along this path, you go to a next state along that path, but things might be different on different branches.
Is there a logic which models asynchronous gates in digital circuits?
Asynchronous gates?
Yes,
So you mean there isn't a clock tick? There isn't a clock tick, right? They're not going according to a clock tick. So what would you need? What sort of stuff would you need?
I'm not sure what I've been told that the main reason why Intel like to make chips like this is hard.
Because it's hard.
So you need somebody.
No. You can check race conditions using these logics as well, right? So one solution is, suppose it's asynchronous, right? So what you do is you make the clock tick so small. If you make the clock tick a millionth of a second or a billionth of a second or something like that, you might be able to essentially get it so that the clock tick is irrelevant, right? That's one way. I can't tell you off the top of my head. Right? Might be worth looking into. Any other questions?
Bigger network.
So by the way, this was a PhD project, right? The student that wrote this, this was part of his PhD. So basically, you can write programs as well as, prove theorems in our group. That's the idea. We're a computational logic group. So it's not just theory.
Is that program open source?
Yeah, it's on my homepage if you want. Email me, right, if you have any problems. It's written in OCaml, but someone's hungry, so how about with that? I'm happy to hang around afterwards, right? So,
Can you please join me and thank Mr. Gore for the wonderful talk?
oh, okay. Thank you.